Welcome to Get Your FRQ On. This question is from the 2008 exam. It is question 5 and it is not calculator active. In the question stem, we are provided with a differential equation dy dx equals y minus 1 over x squared whenever x is not equal to 0. And in part A, we are asked to sketch the slope field for this particular differential equation on the points provided. So with any slope field question, we use the coordinates of the points provided and use them to calculate the various slopes at those points using the given differential equation. And we do our best to try to approximate those slopes on the slope field. If we do that for this question, we get a slope field that looks like this. Notice that x cannot be 0, so anywhere x is 0, we do not draw any lines. We don't draw vertical lines, we don't draw horizontal lines, we don't draw dashed lines, we do nothing. Do nothing if the differential equation is not defined. Also notice that whenever y is equal to 1 and x is not 0, we have slope 0, so we have horizontal slopes here, here, and here. And then we can use the other coordinates to get the slopes for the other remaining points. In part B, we are asked to find a particular solution to the differential equation y equals f of x given the initial condition that f of 2 is equal to 0. All right, first notice that the differential equation dy dx equals y minus 1 over x squared is separable, and so we would be expected to solve this differential equation using separation of variables. In fact, frequently when you have a free response question with a differential equation that you are asked to solve, if it can be solved using separation of variables, you pretty much have to do it that way. Otherwise, you will fail to earn many points on the free response question. So separation of variables, when it shows up, is going to be the expected method that you use. So in this case, solving for dy on one side, dx on the other side, we get dy over y minus 1 equals dx over x squared. Integrating both sides, we're going to get the natural log of the absolute value of y minus 1 equals negative 1 over x plus a constant. Simplifying this, if we exponentiate both sides, we get the absolute value of y minus 1 equals e to the negative x to the minus 1 plus that constant. Using power rules, e to the negative x minus 1 plus that constant is just e to the constant times e to the negative x to the minus 1. And then we can call that new constant c. Notice the change in subscript here. This c1 is not the same as this c here. This is my final c, so that's why I'm calling it c. Oftentimes you might see that as k or something else. Now, because we know that f of 2 equals 0, we can drop the absolute value here. All right, so y minus 1 is going to equal k times e to the negative x to the minus 1, assuming that k is whichever one of those it needs to be, either the plus or minus version. At this point, we don't really know which one it needs to be, but if we allow for the possibility that it could be either one, we can specify that later. All right, so using the equation y minus 1 equals k times e to the negative x to the minus 1, and the initial condition that f of 2 is equal to 0, plug in 0 for y and 2 for x. 0 minus 1 equals k times e to the negative 1/2. So negative 1 is k over the square root of e, which means k is negative square root of e. That gets us our value of k. So now, if we solve this for y, we get y equals 1 minus the square root of e times e to the negative x to the minus 1, which I can simplify as y equals 1 minus e to the 1/2 minus 1x. Now, there's several ways you could write this correctly. As long as you have the correct solution written in one of those ways, you wouldn't be required to simplify it all the way down. So don't feel the need that you have to, as long as you have the correct function. Really, the only thing you have to watch out for is very typically the expectation is that when you solve a differential equation like this, you do have it solved for y. right? Typically, if you have like y squared equals something that may be frowned upon, you might fail to earn a point if you do that. The expectation is that you would solve it for y and then maybe use an initial condition to determine if you need a positive value or a negative value. All right. Now, since the differential equation has a discontinuity at x equals 0, and the initial condition was for x equals 2, right? So that is now the right-hand side of 0. The domain of our particular solution y equals f of x is restricted to x is greater than 0. Why? Because there's a discontinuity at 0, we don't really know what happens on the other side of that, but we do know that for this particular solution, we did come up with it using a positive value of x. So we have to use the side of the domain there that uses our initial condition. 2 is greater than 0, so we have to restrict our domain to greater than 0 in order to include that part or that initial condition. In part C, we are asked to find the limit as x approaches infinity of our particular solution found in B. All right, so using the function that we found in B, f of x equals 1 minus e to the 1/2 minus 1x. All right, if we take the limit as x approaches infinity of f of x, right, we're going to get the limit as x approaches infinity of 1 minus e to the 1/2 minus 0, which is just 1 minus e to the 1/2.